Hello. In the previous lecture, we were discussing something regards a one-dimensional asymmetric infinite deep square well. In this lecture also, we are going to continue with the same. And yesterday, when I was mentioning a thing, I think I made a mistake. So I apologize for that. And let me correct that mistake here. Okay. So the mistake was actually, I was thinking that in order to solve, in order to prove in order to prove that the boundary condition of psi dash, okay, so in order to prove that boundary condition of psi dash not being used, I took a wrong function here. Basically, I'll tell you why this function is wrong, because overall you have to understand that this function may not be that appropriate. So let us revisit this problem all over again. Okay, so I apologize for the mistake. If you just can just now, if you can pay attention, that would be a great thing for me. Okay, so just pay attention. Okay. So the point was yesterday when I was mentioning this particular point, so I thought that this is an important construction that could have been done. But you have to remember why I was harping on this construction, because I thought somewhere I would be able to prove that g dash x is equal to 0. And from here, I would be able to make an assertion that gx equal to 0. But actually, I forgot to understand that if I take a general structure like this, and if I differentiate it, what will happen? It will it will obviously take psi double dash. That is fine, and but it will also contain this thing. So if you can differentiate, you'll be able to know that this is the structure that you're going to get. However, this is not the structure for a Schrodinger equation. If you want to differentiate, you can differentiate on your own. Like if you want to differentiate g dash x, what you will get? You get simply get e raised to power minus x. Then you'll get psi double dash x minus psi dash x, and then minus e ki power minus x, and then again psi dash x minus of psi x. So basically, this construction would not be appropriate. So yesterday when I was mentioning this construction, so kindly skip this part. So basically, this construction may not work here. Okay, so this construction works. I'm writing this construction works. This construction works if we had a differential equation of this form, d2y upon dx2 minus 2 dy by dx plus y. But this is not the form of the, what you can say, our Schrodinger equation. So what I'll do, I'll go with the basic only. And again, let prove you this, because this is an important part where you should really pay attention, because otherwise exam is fine, but probably in any interview you are going to get stuck. So what was the, so what point I wanted to make, that why the continuity of, psi dash not employed. So this is the central question that I'm trying to answer. So see, so let me solve a differential. So obviously this is your differential equation. Okay, so this is the differential equation where we are interested. And if I want to write the solutions for this, and this is applicable for all x lying between 0 and a, the solution will be of the form a sine kx plus b cos kx. And we already know that if I apply the initial boundary conditions on psi itself, that is psi 0 equal to 0 and as psi a equal to 0, what I will get, I'll simply get my psi x as some root over 2 or a, that is fine. And then I will also get sine, what is that, n pi x upon it. This is something that you already know. But if I also, if I had applied, if I had applied both the boundary conditions psi dash 0 equal to 0 and psi double dash, sorry, psi dash a equal to 0. If I had applied these conditions also, then what would have been the result? So if I apply these two conditions, what will happen? Psi dash 0 means what? Psi dash 0 means, I think this would be equal to what? Okay, so let me keep this in K only. Let me keep this in K. So let me keep this in K so that you will be able to understand that what I want to say. Let me keep this in K only so that you'll be able to understand things. So K is what? K is, I think, 2me upon h ket square root over. Okay. So let me keep things in case. Otherwise, if I make that explicit, then I'll not be able to prove it. So let us say what will happen. Uh, I know that if I place initial conditions, this thing psi 0 equal to 0, that implies uh, b equal to 0. That simply implies that b must be equal to 0. It implies that psi x must be equals to what? A sine kx. Now, if I apply the condition psi dash 0 is equal to 0, what does it mean? It means that I'm talking of a k cos kx equal to 0, right? So this is my equation number 1. And if I talk of sorry, if I talk of psi a equal to 0, what does it mean? It means a sine ka must be equal to 0. That implies that ka must be equal to n pi, and that implies that k must be equal to n pi upon a, right? K equals to n pi upon a. Now, if I use the condition psi dash a equal to 0, it implies what? It implies ka cos ka must be equal to 0, because if I differentiate at a, now the point is that if I use this k at this place, I know that this will give me what? It will give me cos n pi, and cos n pi is what? Minus 1 raised to power n. And it implies what? Then this equation would imply what? This equation would imply ka into minus 1 raised to power n equal to 0. Now I know that a cannot be equal to 0. That is certain. Minus 1 raised to power n must not be equal to 0. That is certain. It implies what? K must be equal to 0. And if I take k equal to 0, then it would correspond to e equal to 0, which is not physically acceptable. Physically acceptable. Or if I take k equal to 0, then my psi x will be equal to 0. Again, not a physically acceptable solution. This is what we were discussing, that if you take all these boundary conditions together, that is psi 0 equal to 0, psi dash 0 equal to 0, psi at a equal to 0, and psi dash at a equal to 0. If you take all these conditions together, what you will get? You will get that your psi must be trivially 0. And psi being trivially 0 is not a correct physically acceptable solution. So whatever I was trying to make a point, this was the point. I have explained it through very easier example, so that you will be able to get it. Otherwise, that would invoke a little bit difficult mathematics. I don't want to get into that. I just want to let you know that anyway, if you take the side dash condition, then for non-trivial solution, or for physically acceptable solutions, for physically acceptable solutions, you have to make it a point that continuity of the solution, sorry, I want to make, for physically acceptable solutions, one has to understand that uh, the continuity of psi dash x cannot be cannot be uh, cannot be used. Is that fine? I mean, is this reasoning fine? I mean, this is quite easily that I've proven. I hope this reasoning is fine. If there is any doubt, kindly let me know. Okay, so this is one thing that we were doing yesterday, and that required a little bit of explanation. I have given that explanation today. And now let us, okay, one more thing from here only one can understand. Let me write that in more general sense. So just give me a minute. Okay, so there are a few things that really need to be addressed. One of the things that I really want to address right now, qualitatively only, uh, that is this. Just give me a minute. Okay, so one more thing one needs giving you as a note only. So here one another thing, one has to understand that there is physically acceptable solution. There is no physically acceptable solution uh, to the infinite deep asymmetric square well with e is equal to 0 and e less than 0. Okay, so when I'll be teaching you Dirac delta function, I will take e less than 0 for bound states. However, here the system would be bound only if e is greater than 0. So the point is this, we'll not be having any physically acceptable solution with e equal to 0 and e less than 0. Okay, this thing I've already proven. Please to understand, already proven. But I'm making a more bolder statement here that there would be no physically acceptable solutions to the infinite deep square well with e equal to 0 and e less than 0. So let me justify this. So you already know that actually solving this particular infinite deep asymmetric square well turns out to be turns out as simple as solving this particular differential equation, right? I mean, this is something that you all will agree. Okay. So in solving this, finding any physically acceptable solution to infinite deep asymmetric square well uh, would would be actually equivalent to solving this problem. Now let us keep e equal to 0 at first. If I keep e equal to 0 at first, what does it imply? It implies that d square psi upon dx square must be equal to 0. And that indeed says that this is a solution. This is what? This is a differential equation for a straight line. So y is equal to mx plus c. Sorry, psi x is equal to mx plus c. Fine. Now let us come back to our initial conditions. I've already stated that initial conditions will only be placed on psi, not on psi dash. Now, if I place psi 0 equal to 0, it implies that my c must be equal to 0. And now if I apply psi a equals to 0, that implies what? That implies m equal to 0. And that certainly would imply that psi x must be equal to 0. Again, not a physically acceptable solution. So if I take e equal to 0, then I will not be able to produce any physically acceptable solution. Rather, I'll get a trivial 0. That doesn't make any sense here. Also, if I take e less than 0, let us say case 1, I'll write here. And if I take another case second, so that would amount to writing e less than 0. Okay, that would amount to writing e less than 0. Okay, if I take e less than 0, then what will happen? Then what will happen? So it will be like d square psi upon dx square is equal to what? It is equal to k square psi. So if e is less than 0, see, if e is less than 0, understand, if e is less than 0, this negative become positive, and that is why I'm writing it as k square. So your k would be equal to root over minus 2me upon h ket square. Now just don't get confused. This negative is not actually taking a root over of negative. This is negative and again negative. So this is positive. So don't worry about it. Overall, the quantity inside is positive. Please do understand. Is that fine? See, E is already negative. Negative becomes positive. So this overall will give you a real solution. So basically, what the solution would be what? This is equals to writing my m square minus k square equal to 0. This is like auxiliary equation to this particular differential equation. Implies m must be equal to plus minus k. So the solutions for this psi x would come out as, I will write some a e ki power of, you can take it as kx minus, sorry, plus b e ki power of minus k. So this will be the, uh, so the wave function would be what? Would be depending upon what? A e ki power kx plus b e ki power minus kx. Now, even if I don't do anything, can this be a solution? Can this be a valid solution? Just think about it. Can this be a valid, physically acceptable solution? Can this be a valid, physically acceptable solutions? Just think about it. See, what we know from our theory basic, that as x tends to infinity, our wave function should decompose towards 0. And if you really think as k tends, k is positive already, you see k is positive. Please do understand. Again, I'm trying to tell you, if e is less than 0, then this negative becomes positive. So just don't get confused. This will not give you any imaginary solution. This will give you real solutions only. So if k is greater than 0, and then psi x, now if you try to take limit x tends to infinity, you can clearly know that this is going to blow up. Here it is. And if you take x tends to minus infinity, then again psi x would blow up, because then this will dominate. Okay, is that clear?
Yes.
Okay, so this is one thing that you need to understand. So overall, if even if you don't apply now, if even if I apply the boundary conditions, let's say, let me apply these boundary conditions. Psi 0 equal to 0 would give me what? It will give me b is equals to minus of a, and that implies that psi x is equal to what? A times e raised to power kx minus e raised to power minus kx. Then you can obviously put your other boundary condition. Please do understand, I'm not using psi dash. Okay, I'm only using the continuity at continuity condition on psi. What it will lead? It will lead to k e to power ka minus, this is it. I think this is equal to 0. And obviously a is not supposed to be equal to 0. Then what it will yield you? It will yield you to e to power 2ka is equal to 1. And e to power 2ka equal to 1 means ka is equal to 0. That implies k equal to 0. And if k is equal to 0, that would imply what? That would again imply that my psi x is equals to what? Trivially 0. Again, not a physically acceptable solution. Now, the point one usually I have found students asking me is that when I teach Dirac delta function, I take e less than 0 and claim that this is what I'm doing for bound states. In Dirac delta function, probably I've done the lectures of it. In Dirac delta potential, whenever I solve the problem, I usually take e less than 0 and claim that this is what I'm doing for bound state. Now, question arises here that why it so happens in one-dimensional deep square infinite well that e greater than 0 renders me a bound state solution. See, if you see the structure of the problem, so the structure of the problem does the so. So if I'm doing this d square psi upon dx square, I've already stated this fact that this is this differential equation here, and this is like root over minus 2me upon h ket square. I already know that e is less than 0. So if e is less than 0, then e modulus is equal to what? Minus of e. So basically, this is equivalent to writing root over 2me modulus upon h ket square. So this is fine. This is something that is something you know. The point is this: if I solve this differential equation for e less than 0 and e equal to 0, that was fine, that we have already done. But if e is greater than 0, what will happen? You take it here. Now this is for e less than 0, but if e is greater than 0, now if e is greater than 0, what will happen? this particular fellow this particular fellow will give him what? D square psi upon dx square. And then this k, if sorry, e is greater than 0, what will happen? This k will become what? Root over minus 2me upon h ket square. Now the point is this: if e is positive, then these solutions will be in the form of iota k or something. Let's say, let me write iota k1. So it will, this will give me plus minus iota k. And now if I solve the differential equation psi x, it will give me the solution of this form: a e to power iota k x plus b e to power minus iota k. And what is e to power iota k e to power minus iota k? You can always write it in form of cos and sines. It will be some linear combination of cos and sines. And I know that what are cos and sines? Sines and cos are both bounded functions. So basically, bound states here would be only coming if you take e greater than 0. Because if you take e less than 0, then you're having exponential solutions. And overall, the boundary condition would then imply psi equal to 0. If e is equal to 0, then straightway it is a constant solution, that is 0. But if you take e greater than 0, then you will get some periodic bounded solutions. So, and these are bound states. So here e greater than 0 gives you the bound states. So it's not that way ki, always that e less than 0 is going to give you a bound state. Here the differential equation, the structure of differential equation is such that if you take e greater than 0, only then your bound state solutions are possible. Okay, so this is what one general uh, thought I thought I should make it, that there would be no physically acceptable solution to a deep infinite symmetric asymmetric square well with e equal to 0 and e less than 0. So this is what I was trying to convey from 2 days. So this is the gist of it. Okay, now already having done all these things, one has to remember that why is it so possible? But why is it so possible? Is it not possible? Sorry, is it not possible to have? Is it not possible to have uh, what you can say eigenstate eigenstate corresponding to n equal to 0? So corresponding to n equal to 0, what will happen? You know that as we are doing, if psi x is equal to what? Root over 2 upon a, and sine n pi x upon n. When we were deriving it, we categorically mentioned that n should belongs to natural number. And I said that psi will be equal to 0 if n equal to 0. So you know that if n is equal to 0, then what will happen? Psi x will become 0. Okay, so this is the problem with the solution, that if you take this kind of thing, then this kind of thing, that is, if you take n equal to 0, this will give you the ground state as psi ground state equal to 0, and it will also give you e equal to 0. Okay, which doesn't which actually is not the right way of physically acceptable solution. So always remember that the lowest energy lowest energy in this cannot be equal to what? Cannot be equal to what? 0. Cannot be equal to 0. There is always some energy, some minimum energy that remains for bound state problems. Uh, because see, uh, why there is no state with zero energy? Why there is no state with zero energy? The point is this: it is going to violate your this is going to violate your Heisenberg principle of uncertainty, because Heisenberg principle of uncertainty. Because Heisenberg principle of uncertainty for quantum system dictates that there should be some uncertainty in momentum. Because if I say that E is equal to 0, then P square upon 2m would be 0. And that implies what? That implies that your particle is at rest. And particle being at rest dictates the determinacy. So basically, you will not have any width in the displacement of the particle. So basically, you will never find in quantum systems that your E is equal to 0. In fact, we'll also see that for macroscopic system also, the lowest energy happens to be not exactly equal to 0, but somehow the magnitude of those energies are so minimal that we take it. But otherwise, always remember that there would be no state with a 0 energy for this infinite square well, because if the particle has a 0 energy, then it will be at the rest, and having at rest implies violation of the Heisenberg principle of uncertainty. Please do remember this. Now, interestingly, this lowest energy is also referred to as 0 point energy. So in fact, for this particular case that we have already done, I'll show you in the next sort of problem I'll give you. And then from that problem itself, or that particular discussion itself, you'll be able to understand that the ground state energy happens to be the 0 point energy for the infinite deep square well. So basically what happens is, just giving you a little bit of understanding, I'll come on this thing, 0 point energy. Okay. So basically what I wanted to convey was that if you localize your particles, basically localizing a particle in confined region, localizing a particle in confined region, what it means? It means that it will obviously acquire what you can say some, if I'm saying that I'm localizing my particle somewhere. So if I take delta x, delta px, even as equal to h cat, I'm just right now not actually doing it to the complete perfection, just making you understand. So if I'm confining a particle, so basically it doesn't mean that x should be very constant. So delta x, already you know that what is the delta x? So delta x would be equals to what? It will be equals to a. And if I'm saying that delta x equal to a, that would give it some finite momentum. So localizing a particle to a limited region or a confined region, it will lead to a finite momentum. Finite momentum. And here in this particular case, that finite momentum would be equals to what? Almost equivalent to h cat upon a. And this in turn would mean some uh, finite kinetic energy of the order of h cat square upon 2ma square. I think square would also come delta p square upon. And if you remember, what was your ground state energy? The ground state energy was almost equivalent to is equal to what? It is equal to pi square h cat square upon 2ma square. So basically, confining a particle in a finite region would give you some 0 point energy, and that 0 point energy is almost in the magnitude, almost equivalent to the your ground state energy for infinite square wave. So always remember, in this particular scenario, the 0 point energy is a non-zero thing, and it will always remain a non-zero thing, because I have already stated that if E equal to 0, then it will violate the Heisenberg principle of uncertainty. So, and that's a very, very accurate and a fundamental principle. You cannot see the violation of it. So the point is this key, anyway, you're going to have some finite energy for the minimum possible, some minimum possible finite energy. So you can say that 0 point energy is nothing, but it is the minimum energy, or you can say it is the minimum energy required for the motion of the particle due to localization. It is the minimum energy uh, required for a particle to be localized. Okay, and this 0 point energy, you will see that we are going to even discuss this case for the harmonic potential and different other things. So this is a characteristic feature of bound potential. So this is a characteristic feature of bound states, or you can say bound state potentials. Okay, so another interesting observation here is that if you really see that what was the uncertainty in momentum, the uncertainty in momentum was almost equivalent to h cat upon a. So a few things that here you can think of is that if width decreases, if the width of the square well decreases, that is the width means what? That is, we are trying to come the particle's position, making it more and more accurate. Okay, so basically by by decreasing the width, we are confining the particle's position. So it will lead to the increase in the uncertainty of moment. Okay, and this will lead to what? This will lead to the increase in the 0 point energy as well. And 0 point energy increase means what? Now particle will make all the more faster motion. So basically, particle will move faster and faster, because delta p is greater, p square upon 2m is greater. So faster and faster. This is one implication that you can really think of. In fact, if a, instead of decreasing, if it increases, then what will happen? 0 point decreases. 0 point energy decreases. It may tend to 0, but it will never be equals to what? Even if you take limit, what you can say, a tends to infinite, then only it can be equal to 0, but there is no such possibility of a equal to infinity. So basically, theoretically, 0 point energy can never be equal to 0. Remember this. So for bound state, 0 point energy will be having some positive value, Okay, and you must be thinking why I'm teaching all this. Basically, this has got enough physical interpretations and physical consequences in the realm of your quantum world, and like, as simple as your atom being stable, as simple as electrons not falling into nucleus, as simple as uh, lattice being in a place. Okay, as simple as helium not getting liquefied at very extremely low temperatures. This is the quite important. This is the reason, that is the existence of finite 0 point energy is the reason why all these physical the consequences that we are going to study in atomic physics, nuclear physics. This is the reason why those manifestations we see. Okay, so this is not that easy. This is not that thing that uh, you can think to not understand. So basically, this is why I have introduced this thing. And the point is this, that another important point that you can really think is that what happens. Let's say if I'm talking of if I'm talking of, let us say, uh, a simple harmonic motion. Simple harmonic motion, I know the potential is what? Potential is half kx square. Okay, so half kx square, you know this thing already. Now, so this I've already written, I think. So just mentioning it, that zero potential energy, zero potential, 0 point energy. I think it has been written somewhere, but still write it. 0 point energy is characteristic of. If I have not written it, please do write it. It is a characteristic feature of bound state potentials. Bound state potentials in quantum mechanics. So basically, in quantum mechanics, wherever we are going to study these bound state potential, we are going to have this thing called this particular characteristic energy, which is a minimum sort of energy required for localization of the particle. So if your particle is localized, if it is bound, then you cannot have a case where your total energy E is zero. Okay. Now, what happens in it? This particular thing, having this particular thing, you know, what I could say, what I wanted to make a point here was a valid point. Was this the okay? So let me just write this 0 point energy. This 0 point energy uh, is um, has important physical consequences. As important physical consequences, like atom being stable and atom being stable, and like what you can say, lattice. Sorry, what you can say. Another was helium not getting frozen, uh, not getting frozen even at extremely low temperatures. Extremely. Okay. Now, what you know in classical mechanics, what happens is in classical mechanics, what happens is that if we have to minimize the energy, so the lowest possible energy, so lowest possible energy is equals to what? It is equals to the uh, minimum of the potential energy. Okay, so this is the minimum of the potential energy, because we know that kinetic energy varies as what? It always varies as p square upon 2m. So kinetic energy minimum would be equal to what? It would be equal to zero. Only when kinetic energy becomes minimum, your lowest possible energy gets achieved, and it is equals to what? It is equals to the minimum value of the potential energy. So the lowest value of total energy is equal to the minimum value of the potential energy. and minimum value of potential energy accompanied with the zero kinetic energy. Okay, so this is one thing. However, in quantum mechanics, what happens is lowest energy lowest energy not only minimizes the potential, not only minimizes the potential, but also minimizes the sum of kinetic plus potential, and this leads to some finite presence of 0 point energy. This leads to some finite presence of 0 point energy. So this is another sharp contrast to your classical mechanics. You can take an example of simple harmonic oscillator and understand this point. If you have certain doubts regards this, I'll let you explain all these things. Right now, we are moving to another topic important, which is called as the expectation values. So I hope this is clear till now. Now let us move to another point, which is called as the expectation value. Expectation values. Okay. So now let us calculate some expectation values. I've already stated the significance of expectation values in quantum mechanics. So nothing remains to be said there. So I will be directly finding some expectation value, and just give me a minute. Okay, so let us do a find first for x and then all those things. Okay, I already stated one of the things, and I know I have proven it also, but again I'll give you. Just think the expectation value, the expectation value, the expectation value of momentum for a real wave function is always zero. For a real wave function is always zero. Always remember this. Why it is always zero? Because I've already stated that Px is equals to what? Minus iota h cat upon, minus iota h cat del by del x. So if I want to find the expectation values, what does it mean? Psi, and then you have this p cap psi. This is what is the expectation value of momentum. Now, if I do it in sense of integral, this would be this psi star p cap, and then you have this psi dx, right? So this is the expectation value of p. Now, if you take this, if you write this thing, this would be like this: 0 to a. Psi star is psi only because psi is real. If psi is a real wave function, okay, and this will be equals to what? Del by del x, and then you have psi dx. Now this is real. This is also real. Both of them are real. This integral will give you a real value. And if this integral gives you a real value, overall this is minus iota h cat. So overall, the value would be a complex valued function. And expectation value can never be a complex function, complex value. It has to be real thing. After it tells you the average value. So basically, it cannot be a complex value. It cannot have a complex. It cannot be expressed in form of complex number. That's not mathematically correct. So therefore, there's only one possibility that this integration turns out to be zero. You can do it on your own also, but directly always remember, whenever you're going to find the expectation value of momentum for a real wave function, it is always going to zero, always going to be zero. So expectation value first, I'm just doing for infinite deep square, infinite deep asymmetric square well, the expectation value of P is always equal to zero. This is something that I'm going to write directly. Now, what would be the expectation value of the position operator? Okay, what is the expectation value of the position operator? So it implies what? Let me write it for the general nth state. This is x cap and then psi n, and I know that psi n is equals to what? Root over 2 upon a, the sine n pi x upon a. This is normalized, so I am not going to divide it by psi n, psi n. So basically, this is fine. This is equivalent to what? This is equivalent to writing integration 0 to a 2 upon a x sine square n pi x upon a dx. And you know that this sine square is what? You can write it as 0 to a. This is 1 upon a, 1 minus cos 2n pi x upon a dx, right? So this is 1 minus, I have forgot to write x numbers. X will come here. So this will give me 1 upon a, integration 0 se lekar a, and then I have this x dx, and then minus integration 0 se a x cos 2n pi x upon a dx. Now this integration would give me what? A upon 2. What about this integration? What about this integration? So let us do this integration somewhere here. So here it is 0 to a. Sorry, x would come out, and this a upon 2n pi, and this sine of 2n pi x upon a. So this will become 0 because anyway sine 2n pi is 0 and then sine 0 is 0. So this part will become 0. The other part will be x derivative is 1. Cos once integrated would give you a upon 2n pi, and I think you will get some sine 2n pi x upon a dx. Again, if you integrate, you will get what? Again, if you integrate, you will get what? You get a square upon 2n pi square, and then you will get cos 2n pi x upon a, and then you will having 0 and you are having 0 and a, some negative positive sign. I'm not bothered about it. 2n pi whole square, this is fine. This integration, just think, this is cos 2n pi minus cos 0. What is cos 2n pi? This is 1. And what is cos 0? 1 minus 1, 0. So this integration would be 0. So forget about this integration. So the expectation value of the position operator, that simply x is given by a upon. Is that fine? I think this is clear. And what would be the expectation value of x squared then? What will be the expectation value of x squared? So expectation value of x squared would be simply 2 upon a, integration 0 to a. I think this will be sine x square, sine square, n pi x upon a dx. This is 1. Okay, and then 2 upon a, then integration 0 to a. I think you can do it on your own now from here. 1 minus cos 2n pi x upon a dx, and I think half here be 1 upon a. So this is 1 over a, and this integration would give you a cube upon 3 minus integration 0 to a x square cos 2n pi x. This integration we have to do. This integration we'll have to do. So let us do this integration somewhere else. So let us do this integration here. So what it will become? It will become x square stays at its place, and then it will become sine 2n pi x upon a. From 0 to a, this will give me 0. So I'm not bothered about it. The next part would be what? There is a negative here, so I'll just use positive. Integration 0 to a. This will become 2x. And integration of cos is sine. So it will become a upon 2n pi. And then I will write sine of 2n pi x upon a dx. And again, if you think, again, if you try to solve this integration, so this will become 2a upon 2n pi, and then this integration again, I'm making a bigger bracket, and then I'm solving. This x will remain at its place. Sine would give you a upon 2n pi cos of 2n pi x upon a, and from where to where? From 0 to a, in fact. Okay, and then negative of sorry, this will become 0. Then again negative of a upon 2n pi. This will become 0 because cos 0 is 0, cos 0 is 1, and cos 2n pi. Achha, okay, no. This will remain. This will remain. Sorry. So sorry. There would be some term here. I have to take care of that. So sorry. Okay, This will give you some term, sorry. Now, another term would be what? Another term would be, sorry, this pen here. Another term would be minus of a upon 2n pi. And I think 2 will also come out. 2 will also come out. X I've already taken. Now, integration of x is, the derivative of x is 1. Integral of sine 2n pi would give you again something like a upon 2n pi, and this will become positive. Cos of 2n pi x upon a dx. I think this integration will become 0 because you have this cos integration is sine 2n pi 0, sine 0 is 0. So I think this you don't need to bother about. I think here it is, if you write 0 here, so this will become 0. If you write a here with a negative sign, so what you're going to get, you're going to get a square upon 3 minus, this minus I've already taken. So don't worry, this minus I'm taking because I'm using the lower limits now. It will get a upon n pi times a square upon 2n pi, and cos 2n pi is always 1, so that's not a problem. So you will get expectation value of x square turns out to be a square upon 3 minus of uh, okay, so this 1 upon a here also, sorry, 1 upon a here also come. So it will be a square upon, this 1 upon a will be here also, right? So 1 upon a here also, 1 upon a here also it become. So this 1 upon a and a cancels. A square upon, this will turn out to be 2 n square pi square. Okay, so this is the answer. So expectation value of x square is a square upon 3 minus a square upon 2n square pi square. Okay. Now expectation value of p I've already stated, it is 0. What would be the expectation value of p square? So what would be the expectation value of p square? Okay, so expectation value of p square is equivalent to writing psi n, p square psi n, and it will be equivalent to writing minus h cat square integration from 0 to a psi n star, which will be psi n, and d square psi n upon dx square and then dx. And because see, at the end you have to understand that this is d square psi n upon dx square. I think what I should write. Okay, so if you remember, your psi n was if you remember psi n uh, minus h cat, how, what was it? I think if you remember, it was equal to what? Just give me a minute. Psi n double dash, it was equal to k square psi. I think this was it, right? This was it. If you remember, this is something you know. And k square is what? K square is 2m e. Now instead of e, you can write n upon h cat. And if you write e, e will be equals to what? E is n square pi square h cat square upon twice ma square upon h cat. So this k square I can also write it as m cancels m, 2 cancels 2. So this is equal to n square pi square h cat upon a square. H cat square or what? Uh, so there is some mistake. No, so k square is fine. Okay, let me do it directly only. I thought I would be able to do it in a better way, but um, 2 men upon h cat. This was it or something else was. Just let me see. H cat square. Sorry. So there is h cat square here. My bad. Okay, so what I was trying to do, so that at times you can use some differential equation. That's why I was doing this. See, why I'm not doing it in the lengthier way. Obviously, see, one has to understand that psi x, if it is sinusoidal, if you differentiate it twice, it will come to the same. Let's say if you're using sine once differentiated cos, again differentiated sine. Okay, so that is the magic of mathematics. So that is what I was trying to do. See, if you don't want to do it in a very lengthier way, understand that anyway, psi n is a solution for the differential equation. What differential equation? Minus h cat square upon twice m psi n double dash is equal to what? I think is en psi n. This is this is the this is your Schrodinger equation corresponding to the infinite deep square value. Okay, so basically you know that this psi n dash solves this differential equation. So psi n dash you can straightway write it as 2m upon, sorry, uh, what it would be, uh, n square pi square h cat square upon twice ma square psi n. So basically psi n dash double dash you can directly write it as 2m cancels 2m. You can write it as n square pi square psi n. So I'm going to write it as p square is equal to what? It is equal to minus h cat square. Uh, what was the differential? I remember. Just give me a minute. So that, okay, minus here. So sorry. So sorry for this. I think negative when I am multiplying, so it will be here. It will be here. So it is minus of n square pi square h cat square cancels psi n. So basically what I'm going to do is, instead of this psi n double dash, what I'm going to write, integration 0 to a psi n star remains here. Instead of d2 psi n upon dx square, you can straightway write minus minus plus n square pi square, and then there is a square also, a square also upon a square, and then you have this psi n. And you know that your psi n is normalized, this will become equal to 1. So simply p square expectation value turns out to be n square pi square h cat square upon a square. Okay, so this is your expectation value of p square. I hope it is clear. Why I'm so interested in this, I'll let you know. This is one thing that you should remember. Okay. Now, if I want to write the uncertainties in uh, position and momentum, so delta xn would be equals to what? You know that uncertainty is given by this variance. This is equals to psi n x square psi n minus psi n. I hope I have taught you Schrodinger, sorry, uncertainty principle. If I have not, then I'll teach you. In the, I think this is something that you should all know by now. So delta x and then would be equals to what? That it will be equals to root over. This is, I think, if you remember, this was a square by 3 minus a square upon 2i's n square pi square minus this was a by 2, so this will become a square upon 4. So this will, if you take a common out, so this will become a root over, this is 1 by 3 minus 1 by 4. This is 1 by 12 minus 1 upon 2 n square pi square. And what will be this uncertainty in momentum? It will be equals to root over. Simply this will become 0. So it will be psi n p square psi n. And I know that this is equals to n pi h cat upon a simply. And what would be this product? Delta xn into delta pn. This will be equals to n pi h cat upon a. And a cancels out. It will be equals to root over 1 upon 12 minus 1 upon 2n square pi square. So this is the product of uncertainties in momentum and this thing, delta xn into delta p. Is that fine? And if you really want to know what would be the uncertainty in the ground state, so uncertainty in the ground state, I'm writing uncertainty in the ground state would be uncertainty of momentum in ground state will be equals to what? Instead of n, you have to write 1. So pi h cat upon a simply. And this minimum, this will lead to what? This will lead to minimum non-zero kinetic energy. And what is minimum non-zero kinetic energy here? The minimum non-zero kinetic energy will be delta P1 square upon 2m. So that will be like pi square hk square upon twice ma square. So basically, your minimum particle's kinetic energy is of the order of pi square hk square upon twice ma square, and this minimum kinetic energy is the minimum kinetic energy. What is this? Basically, this is like localizing your particle. This is equivalent to localizing your particle in the width a. So this minimum non-zero kinetic energy referred, it can also be referred to as the 0 point energy. And coincidentally, this also happens to be a to minimized ground state. So your minimum total energy also corresponds to the minimum of the kinetic energy here. Okay, so this is what I was trying to refer, that the 0 point energy for your one-dimensional infinite deep square well turns out to be almost equivalent to the ground state. Also turns out to be the what you can say, the ground state of the, so 0 point energy is equivalent to the ground state of the uh, deep infinite square well. An interesting observation, another interesting observation I'm going to do, and then I'll conclude the lecture. The interesting observation here is that if you really wanted to find the average value classically, if you want to find the classical average value, or you can say classical momentum average value, what would it would be? So you know that the particle is confined in the well. So if it moves towards the right, move towards the left, then the momentum would be minus mv, and if it moves towards the right, then the momentum would be plus mv, because there is no influence of any force. So mv minus mv. So net average, uh, what you can say, the average momentum here would be also zero. Classically, average momentum would also be zero. However, uh, if you want to find what would be the average value of what you can say, and why I'm saying this, Vx is zero, so net external force is zero. So therefore, you can you know that particle moves towards the left, then the vectorially the momentum would be minus mv, towards right vectorially it would be plus mv. So net average momentum would be zero. Now, what about the if the since the particle is moving in the constant with the constant speed, because the net force is zero, so it will move with the constant speed. You know that x can be written as v into t simply, and then x average you can calculate. It would come out to be equals to 1 upon t, 0 to t xt dt. If I want to average it with respect to the time, then I've already stated the average value function. Always remember it is equal to integration 0 से लेकर t, or whatever value you have. Let's say you want to integrate from 0 to capital T, ft dt divided by t. So this will give you, or integration dt. Always remember this is the average value of the any function. Uh, Okay, so average value function is given by this expression. This is average value theorem in integral calculus. So I'm not referring the complete theorem, just writing it. If ft is continuous function, if you want to find this average value, then you can find using this integral. And you know already xt is what, vt. So it will give you what? It will give you, I think, a upon. Average value classically. And this is in the 1/2 of the period. So we are moving from, okay, so from here to here. And if you come back again, then the average, because displacement then would become zero. So I'm just calculating for 1/2 of the period. So I'm calculating this for the, this t happens to be the half of the period of the motion. Otherwise, it will become zero. Half of the period of the motion. Half of the period of the motion. If I calculate x square average classically, what it will be equals to 0 to t. 1 upon t comes out, and this is like b square t square dt, right? And this will give me what? It will give me 1 upon t. V square will come out because it is a constant. And what is t square? integration, this will be t cube upon 3. So this will be equals to v square t square upon 3, and v square t square is what? It is equal to a square upon 3. Okay, now let us try to compare this particular thing. So x square average turns out to be a square upon 3 minus a square upon 2n square pi square. So clearly, if I take limit n tends to infinity, on the average value quantum mechanically, I'm going to get the a square upon 3, and which is the classical average value. Okay, so in the limit of large quantum numbers, your classical, the quantum mechanical average x square would come out equivalent to the classical average. I hope I am able to make some sense till now. So this was something regards the expectation value, a little bit about 0 point energy, and a little bit about the yesterday's lecture. If you have any doubt, difficulty, kindly let me know. At times I go a little fast, but the point is I have to finish things off. So you just read all these things, and once you just make kind of notes from these, and then if you have any doubt, kindly let me know. Okay, so that would be fine.